Okay, so hopefully we're going to be able to finish the hands-on lecture series today. So we left off in the first little book about walking you through PyTorch. So let's go ahead and connect. Okay, one announcement before we get started. So we wanted to finalize the teams, but there's this one guy who's not responding, and the drop deadline, I think, is passed. So I don't know if we should include him in one of the teams, in one of the random teams. There's 135 students enrolled, and 134 are already assigned to a team, except for one person who's not receiving our calls or emails. So we'll ask our department office on how to proceed, and after that, as soon as that person is resolved, we should be able to finalize the teams and allocate GPUs. Any suggestions on how to proceed in this case? Should we do a Russian roulette and randomly assign the person to a team? Okay, anyhow, let's finish 13.1, the PyTorch lecture. Yeah, so we talked about NVIDIA SMI for checking the current status. Important parts are this line here, how much GPU memory you're using. You're going to see lots of OOM, out of memory errors if you don't consistently monitor this. And here, this line, it shows you how many jobs are running in certain GPU IDs. And if you run this just aside, if you run on-premise GPU servers, then this is a noteworthy attribute as well. Here we're going to use dedicated GPU servers. I think it's well maintained, but if you run your own GPU servers, you need to pay lots of attention to cooling, because this is the temperature for that specific GPU. And if you don't really maintain the GPU server room very well in terms of cooling, it's very easy for this number to go above 70 degrees. So in that case, it's going to start melting your circuit board or whatever, and everything's going to shut down. And I think towards, I hope this doesn't happen, but towards the summer, Seoul National University doesn't do a really good job in maintaining GPU servers. So it's possible that this number goes above 70, 80 degrees and shut down, because I think once every summer, GPU servers all shut down in Seoul National University. Watch out for that. But if you use cloud GPUs, you don't need to worry about this. Okay, so we introduced PyTorch neural network module where you can instantiate linear, and we built MLPs together, and this is an example 3-layer MLP with 3 linear weights and activation. It also provides you with various activation functions. And yeah, this is important. So if you fine-tune your models, it's very, very important that you occasionally save your model weights to your designated hard disk, so that in case, I don't know, your Docker instance crashes, or computer shuts down, or whatever, or there's an earthquake, then weights are saved. So when you rerun your jobs, you can pick up from wherever you left off, doing torch.load and the file name, and that's going to be the weights. And you create your empty model, randomly initialized, and you call load state dict with the weights. And this is going to overwrite the randomly initialized weights with whatever's written in that save file. So you need to do this occasionally if you don't want to lose all your progress. And for example, if you work at a tech company, then you'll be launching jobs as servers, and typically research teams have low priority. So GPU servers have what's called priority, and it's priority-based queue. And some product teams have higher priority. And when product team launches some jobs, your research code will crash, and that's just the way it is. And you gotta prepare for that. So you gotta assume your job is going to be interrupted at any minute. So you should be consistently saving your model files to disk. And when your jobs get interrupted, then you should design your code in such a way that it starts off checking for the latest checkpoint file. So look at when the file is saved, and start from the latest available checkpoint. And in practice, that in and of itself is not sufficient. You need to also save the optimizer state, right? Because loading the weights to whatever you left off is that's one thing. The other is, say you're doing atom optimizer, then you don't want to start your learning rate schedule from zero, from the early iteration 1. You are in the middle of the training procedure at a very certain learning rate and optimizer states like momentum, velocity, everything. So that's also got to be saved. So this in and of itself is insufficient. Okay? Does it make sense? All right. So that's going to be a lot to save. Okay. All right, so blah, blah, MLP, we did for call, and yeah, so how do you compute the gradient? It's very simple. So you call backward function, and the gradient is stored in each tensor's .grad member variable. So let's, for example, create some random tensor, and our loss is square L2 loss here. And let's do dot backward and numerically verify it and check whether it's close to our analytic gradient, which is 2 times x. And we've done, this is final loss scalar. We did backward, and when we created this tensor x, we said required grad true, default as false. So when you set this to true, x is going to have as a member variable .grad attribute. So we're going to see if the actual gradient computed by PyTorch is pretty much the same as the analytic gradient, and answer is yes. Okay, so optimizers. Previously, we created our own optimizers, but in real life, we don't really need to, because everything is provided for you, and torch.optim, this is how you initialize your optimizer. So you can do SGD, Atom, RMS prop, whatever you want. Give it the model parameters and initial learning rate. So in optimizers, the most important hyperparameter is the initial learning rate. Things like momentum 0.999, things like this, you don't need to touch it. It's a waste of time. And it's very critical how you set your initial learning rate. So this is the most important hyperparameter among everything else. Okay. Okay, so and the loss, you can do functional, or you can use it from NN. It has MSE loss, cross entropy loss, hinge loss. Everything is available. Just give it the model output and target, and it's going to compute the loss. And this is also important. You need to make sure you do optimizer.zero grad per each gradient call. What this does is, without this, the gradients will be accumulated. So why would you want your gradients to accumulate? It's because, let's say you have an extremely big model, and you cannot do batching because it blows up the GPU memory. So one of the workaround is to do multiple for calls and average the results. That's going to be same as one single for pass with large batch size. So let's say I want to do batch size 1, do a for call 10 times, for backward 10 times, and average the gradients, average the 10 gradients. That's going to be same as average batch gradient with one for call batch size 10. You sometimes want to do this when model size becomes too big. So this is a useful feature, but for simple cases, you don't need to. So you always need to call .zero grid to disable gradient accumulation. And from the loss, you do a dot backward. It's going to compute the gradients and execute optimizer dot step, and it's going to take care of applying the gradient update. For SGD, it was very simple, but for Atom RMS prop, it was quite complicated. You need to maintain the state of velocity and momentum, everything. But this single line takes care of everything. All right. Okay, so we're going to train our MLP to fit a sine function, y equals sine x, using Atom Optimizer. So we're going to use a simple MLP model and create some training data. So x is some random x, y is a sine of that. And we're going to use Atom Optimizer with MLP parameters. And for 1,000 steps, we're going to apply Atom updates. And for each x, we're going to compute the output. And this is the output of the neural network. And this is the target, the actual ground truth. And we're going to disable gradient accumulation and compute the backward for all the parameters. And we're going to do optimizer.step to apply gradient updates. And we're going to keep a list of the current losses and make sure it goes down well. Okay, it seems to be going down really well. So I think I said this many times, but just to reiterate, Machine Learning 101 is first thing you want to make sure you can overfit to the training set. You want to make sure your loss go down very well on training set. If you're stuck there, then there's no point looking at the test error. Okay. So if you can overfit to the training set, then next turn is to monitor the loss on previously unseen held up data set. All right. So let's also plot the loss curve. Looks like MSE loss is going down very well. And that's actually tested on previously unseen X. So we're going to do a uniform grid of X. And for training, we used as X some random numbers. But here for testing, we're going to do a uniform grid and compute the sign and compare the actual Y with respect to the trained Y prediction. Okay, seems to be working very well. So x-axis is X, y-axis is both Y and Y prediction. Yeah, looks pretty good. Okay, another thing is the GPU acceleration. So for the project and homeworks, it's going to be almost impossible to do anything without GPUs because there's about 2 orders of magnitude difference in terms of wall clock time efficiency, at least. So you need to make sure you don't move around these heavy tensors between CPU and GPU that much, because that's going to create data moving bottleneck. So you need to be cautious about where your tensors are stored. And if possible, you need to maintain the tensors in the GPU memory as much as possible. So if you do torch.device and string this GPU ID, then if you have multiple GPUs, then you can do, for example, you want to use GPU ID number 2, you can do torch.device CUDA : 2. So this number corresponds to all the way back in NVIDIA SNU, this number here. So if you have multiple GPUs, you're going to have 0, 1, 2, 3, 4. Each is going to show how much GPU memory is available, what the temperature is, what kind of job is running, everything here. Okay, let's see. So first do device equals torch.device CUDA 0. Let's say we want to use the first GPU. And you can do something like this to device. This is going to create a tensor and move it to your designated device. But you can just create your tensors directly to GPUs. So when you do torch.some tensor creation, provide it as a flag specific GPU ID. And if you apply some operations on whatever is in GPU memory, the default is to store the output in GPU memory. So if you apply some operations on X, Y is going to get stored on GPU by default. And what if you want to move model parameters to GPU? Then you can do to MLP.to some device ID, and it's going to move the model weights to GPUs. And so if you print out by querying the dot device attribute, it's going to show you everything is in CUDA 0, meaning the first GPU in the server. So here we provided an exercise, not for you, but just for reference. We're going to do some model training and actually see how much speed up we get by running things on CPU versus GPU. So first, it's running everything on CPU. So in the meantime, what do? You're monitoring your training loss. It's not going down very well. What do you do? Anyone? Change the optimizer. Can you be more specific? You mean changing from Atom to RMS prop or something like this? Your default is going to be Atom or RMS prop, and you're not going to change that. It works so well. So. Yes? Can you speak up? Increase the learning rate. Yeah, that's the first thing to do, but not necessarily increase. It's most likely you're gonna have to increase, but just in case, just try multiple initial learning rates. What else? Increase the model size. Yeah, that's another good direction. Yeah, try different learning rate. Right? Try different learning rate. Try different model. What else? Yes. Increase batch size. Right. So that's another important thing. So here, monitor NVIDIA SMI. Do some training loop. You just execute training for some specific batch size. If you have room available, you should try to max out this number as much as possible. And one easy way to do this is to reduce the variance of the gradient by increasing the batch size. So if you have a lot of empty room here, there's no reason not to increase batch size. So you should do this if you have a room in GPU memory. Okay, what else? Yes? I'm sorry, can you speak up? I heard something wrong or not. You need to check if there's something wrong or not. Like, what can go wrong? Yeah, there can be some human errors, like especially I've seen this happen many times, is you're using the wrong tokenizer. So model is trained specifically using tokenizer ABCD version 10.4, and you download the model from Hugging Face, and you're using some other random tokenizer, the state-of-the-art tokenizer version 55 or something like this, and model has never seen this tokenizer, so to the model it looks like you're inputting some random characters, so you get almost random accuracy. That's a very common source of error. What else? Okay, so there are many things that can go wrong, and you need to pay extreme attention to the details. But I can tell you right off the bat what not to worry about. Stick with error optimizer or RMS prop and don't bother. And try to increase the batch size as much as possible until your GPU throws up out of memory error. Out of memory error. Increase batch size as much as possible. And try different learning rates. And see if you can do data augmentation. So one way to do this is to increase more variation in the training set. So can you provide more data set? Yeah. All right. So let's see. So first up, we use CPU. Next, this is running CUDA 0, the first GPU in the server, and the wall clock time difference was about 70 seconds versus 2 seconds. So the ratio between this number and this number is going to get larger and larger if you use more high-end GPUs. And for project, we're going to supply L40s, which is one of the high-end GPU servers. Okay, so let's open up our second and final notebook. Okay, so how many of you have heard about Hugging Face? Oh, wow, a lot. Okay, so Hugging Face is a company and an open source platform where people upload their models, data sets, and tasks, leaderboards, all sorts of things. So chances are you're going to download a pre-trained model from Hugging Face for a project. So here we're going to cover downloading pre-trained model, tokenizers, generate some text, and download some data set, and do some pre-processing on the data set and fine-tuning. Okay, so he says navigate to edit notebook settings for the GPU. We are assigned to this T4 GPU. I think this stands for Google TPU. Okay, let's do NVIDIA SMI again. Okay. And connect. And I think the TA have changed the notebook slightly this morning. So in case you downloaded it yesterday, you need to re-download it. Okay. So Hugging Face, you can look at their documentation after the lecture. So has the Transformers API, where you can import the models and tokenizer, and we're going to also import Torch. So for this exercise, we're going to load from Hugging Face OpenAI ChatGPT 2. So this is the interface provided by Hugging Face. You do auto model for causal LM and from pre-trained model. And model ID is this string here, OpenAI community, GPT-2. And we're going to use float 16. And you don't have to. You can use what's called quantized models. We're going to cover this in the theoretical lectures for efficiency. And also for the tokenizer, we're going to use auto tokenizer from pre-trained model ID. And I've seen this happen many times. You need to pay extra attention and make sure whatever model you're loading is compatible with whatever tokenizer you're using. So during training, which tokenizer it has seen has to match during inferences as well. Okay. So let's use the loaded tokenizer and insert some string. So this is an example string. We're going to tokenize it and see what it outputs. So we provided some random string, and it tokenized it with a sequence of integers. And if we decode it, it broke it in terms of my name is chat GPT dot etc. So you can ask it. You can ask the tokenizer to output it as a PyTorch tensor by providing this input return tensor equals PT. Otherwise, I think the default is to return it as a list. So for tokenizer, this is the standard usage. You insert some text and make sure you return the tensor as PyTorch tensor and move it to our GPU and provide it as input to our model that's loaded from some pre-trained checkpoint. And let's crack open what's inside these. So for example, for tokenizer, if I just print the tokenizer itself, it's a dictionary of input IDs and attention mask. Input IDs is a tokenizer presentation of the input text, up size, batch size, sequence length. Attention mask is the binary mask. where 1 is you can attend to the token, 0 you cannot. And so, for example, if you have causal mask, you should have zeros when to prevent it from looking into the future. So, yeah, turns out this outputs a dictionary of input IDs, which are just token representation and then corresponding attention mask. And what if you want to do batching? Then you're going to have attention mask and token length that's different across batch dimension. But of course, we want to do parallel processing using GPU. So what we're going to do is do padding. And by default, we're going to pad to the left. So, for example, if we have 2 texts here of different size, we want to just make sure everything's 0 padded and equal sized. So first text is 13 characters or 13 tokens, and second one is 4 tokens, so they have a different size. And we're gonna use end of sentence token to pad the tokens first. So here, I guess this number corresponds to the end of sentence token for this specific tokenizer. So you can see the shorter string is pre-padded with end of sentence token, which in this tokenizer has this number here, 50256. And we're going to specifically say pad to the left. Same thing for the tokenizer. We're going to pre-pad it with 0 for the shorter string. Okay. So here, when we call the tokenizer, we provide a list of inputs, return tensor, PyTorch tensor, padding true. For the padding attributes, we set it here. We're going to pad it with end of sentence token and pad to the left. Okay, so how do you provide it as input? Here, this line is copy pasted from above. We're going to do star inputs to the model. And what does the model have inside? Model output have inside. Has some keys. It's also a dictionary. Has logits and past key values. And logit shape is upsize, batch size, sequence length, and vocabulary size. Batch size was 2 because we provided a list of 2 texts. And a sequence length is 13 because the longest one here was 13. And vocabulary size because it outputs logits for the next token. Okay, so you can also provide your custom labels during forward pass. Then it will automatically compute negative log likelihood loss for you. And say you want to do autoregressive training using causal mask, then if label is not provided from outside, then we talked about this before in the lecture. So we shift labels by 1, right? Because it's predicting the immediately following token, and we can apply cross entropy loss, and using the cross entropy loss, we can look at the loss, comparing the logits with the one-hot labels. So here, this line is same as before, tokenizer with padding true, and if you provide inputs, it's automatically going to compute the negative log likelihood as the loss. So here, if you look at visualize the output keys, I have loss, logits, and past key values. And if you visualize output.loss, it's a PyTorch tensor with this number is a negative log likelihood, and gradient function tells you it was negative log likelihood loss. Okay. So a lot of the stuff we have to do manually is already being done underneath the hood for you. So let's do some generation. So we loaded the tokenizer and we loaded some pre-trained GPT-2 model, and let's generate some text. Let's give it some context. It's going to pre-fill in the memory and start generating text one at a time. So in the lectures, we talked about greedy sampling, beam search, top K, top P, etc. So you can ask the interface, Hugging Face interface, to generate using specific sampling strategy via generation config class. So here, we're going to tokenize the input context, machine learning is, and we're going to provide the generation configs. So we're going to stop when a new line character is generated, and max new tokens, we're going to only generate up to 30 tokens, and we're going to pad with end of sentence tokens because I don't know, it might have different input sizes. And for now, we're not going to do batching, so this is not really doing anything. So we're going to do model.generate, give it some input context. This is going to get pre-filled, and we're going to auto-regressively generate one token at a time. And for sampling strategy, this is what we're going to modify. And for tokenizer, this line is this is the context, return tensor, device, blah blah blah. So with greedy sampling strategy, it says machine learning is, this is the input context, and from here, these are the tokens generated one at a time, already regressively, and I think it outputted something that's sensible. Okay, how about beam search? So again, we're going to modify this generation config class. So 10 beam, we're going to use 10 beams, maximum 30 tokens to generate, and end of sentence token. And there is a hard constraint that says do not repeat the same token 3 times. Okay, it says machine learning is one of the best ways to learn about the world around us. We're excited to share it with you today, blah, 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 blah. And how about top K sampling? So here we're going to use top K of 100. So this restricts sampling to 100 most probable tokens, and you sample from those top 100 and etc. Machine learning is a fundamental aspect. Yeah, it outputs something, but I don't know why there's University of Wisconsin. Okay, it's funny. Top P sampling, this is the nucleus sampling we talked about. You restrict the support from the probability mass up until it sums just above 0.95, and designed for developing autonomous cars, build intelligent car, would use for any automobile, etc. Okay, so this is how you generate, given some context. Okay, so let's download some data set and try to do some processing. So this is the, if you click the link here, there's more context here. So this is a data set that looks like this. It has instruction, input, output, text. instruction, for example, here, give me 3 tips for staying healthy. Eat balanced diet, exercise, get enough sleep. And text, this is, these are some input prompts that you're going to give to the model. Below is an instruction that describes the task. Write a response that appropriately completes the request. Instruction, give me 3 tips for staying healthy. Response, blah, blah, blah. And sometimes you will have this optional input attribute. Says identify the odd one out. Twitter, Instagram, Telegram. Oh, wow, this is challenging. Answer is Telegram. And below is the instruction that describes the text paired with input that provides further context. So input prompt is different when you have this optional input flag. Why is Telegram the answer? Yes. Telegram is encrypted. Okay.
Especially like Instagram, I think they're probably going to change their DM messages to not be encrypted anymore. So, I mean, privacy-wise, it's not good, but
I see.
that has Telegram is safe.
I see. Okay, so we're going to load the alpaca dataset. And let's print what's inside here. So we're going to look at the first training example. So dataset object has train split, instruction, input, output, text, attributes, and about 50,000 data points. And the first one looks like this: instruction, input, output, text. Text has these prompts: write a response that appropriately completes the request. And input is the optional context for some of the tasks. So it says about 40% of examples have these optional input, and they have different prompts for text. So when you want indexing, you can do it like this. Bracket train, 0 text, text train, train text 0. They all give you the same thing. And from this alpaca dataset, we're going to load it and do some processing with it. So before we do some processing, just to give you some context, you can create some dataset on your own, some custom dataset in memory, like following. So create from datasets, import dataset, and you provide lists of dictionary with respective attributes: input and output, hello world, welcome to deep learning class. And you do dataset from list and provide your custom training data list. So this is how you create your own dataset. And here, okay, we're going to do some processing on the dataset. So we downloaded the alpaca dataset, and we're going to introduce these functions: shuffle, map, and filter. So map and filter are useful functions if you want to do pre-processing on the given dataset. So this applies to individual data points. So in case of map, it returns a dictionary containing new or modified fields. And filter, if you want to filter out some of the data points, this can be useful. So here, what we're going to do is we're going to first shuffle the training split and construct the instruction prompts for the fine-tuning. And notice the instruction prompts were different whether it had input attribute or not. So we're going to also tokenize the inputs, and we're going to filter out actually the examples. If the example had too much token beyond the maximum token length, then we're going to just get rid of the example. So what do I mean by maximum token length? So this specific model, when it's trained, there was a hard limit on how many tokens it saw during training. So for example, if it only saw like 10,000 up to 10,000 tokens during training, during inference, if you supply like 5,000 tokens, then you cannot guarantee what it's going to output. So you want to filter out the examples that exceed model's maximum sequence length. So we're going to do all these pre-processing. Why? Because we want to fine-tune our model on this specific alpaca dataset, so that it can, upon receiving these prompts, it can correctly answer the prompts. Okay, so we're going to have two instructions, one with input. So when the data has input attribute, we're going to change the prompt like this, pair with input that further provides context. When it doesn't have input, we're going to simply say instruction given context, completed. And it's going to have the form, instruction, input, output. When it has input, otherwise, it's just going to have instruction output. Okay, so we created this create prompt function, tokenize function, and filter function. Create prompt when this data point has input key available, then we're gonna, when it's not available, we're gonna use the prompt without the input and provide that specific example's instruction and output. When it has input, we're going to use this prompt specialized that can handle input. Okay, and text is going to be, text attribute is, this wasn't contained in the data set, so this is what we're going to create here. So these text. And filter, tokenize is obvious, we've done this. And filter, we're going to check individual data points and check the length. And if the token length is greater than model's maximum token length, we're going to filter it out. So given these implementations, this single line of code will do everything for you. So data set, we're going to take this training split of data set and shuffle it with some seed ID for random shuffle. And we're going to use the map functions for these two functions we created. Create prompt for creating the text attribute with the instruction prompts, and tokenize, and we're also going to use dot filter to filter out long examples. Right, this was an example data that we loaded, instruction, input, output, and it was missing this instruction prompts. And this is what we're creating right now. Right, so take some time. Looks like maximum sequence length is 1,024 tokens. Okay, it's done. And before fine-tuning, we're going to see how well it performs. So for the GPT-2 model, let's give it some example prompt. So our instruction prompt is following. Below is an instruction that describes a task. write a response appropriately. Instruction is explain what computer science is. And this entire thing is a given context, and it's supposed to generate the tokens that follow these contexts. Okay, so this is what we're going to provide as input to our GPT-2 model as context. For generation, we're going to use this generation config, so top P sampling and up to 80 tokens to generate, and we're going to provide this input prompt and to top P sampling. Okay, so before fine-tuning, this is what we give. So this was the input instruction prompt, and this is what it generated. Writer counter for computer science, event response. Writer counter for computer science. Yeah, it generated something that's not very good. So here, we're going to let the model see these examples from the alpaca data set and fine-tune it. Okay, so for this model, so how do you train the model? Then the way to do this is use training arguments class from the trainer interface from the Hugging Face. So these flags, you can look it up after the lecture. I'm going to skip the details. Okay, so prepare the data and so for batching, you can use what's called data collator. And specific details, I think it's just too much detail to cover in the lecture. So it will do padding and add labels and prepare the data so you can use it during training. I think specific details are not important. So here, this is what you need to actually start training. So you need the trainer object and give it the model training arguments. This guy here, output of the training arguments. So how many steps you want to train, where do you want to save the output, how often you want to log, things like this. And you want to provide the tokenized data set we just created together and the collator for batching and padding. And how do you train? Simple, trainer.train. And it's going to train for how many steps? 500 steps. And it's going to use batch size of 1 and log the progress every 50 iterations. And it's going to do gradient accumulation of 2. So it's going to do 2 for call to compute 1 gradient. Sometimes if you want to use extremely large model, there's no other choice than to do gradient accumulation. Everyone follow what's being done here? So data set has insertion, input, output. These text, we created them together with map and filter functions. And we're doing fine-tuning on GPT-2 so that given the instruction prompts up to here, it's getting penalized for answering the response differently. It's maximizing the likelihood for these responses. Looks like it's almost done. 500 steps, right? Okay, so same thing, same prompt that we showed the GPT-2 model without fine-tuning. We're going to provide exactly same prompt here. Below the instruction, describe the text, write a response. Instruction is explain what computer science is. And same generation config, we're going to do exactly same decoding, top P sampling of 0.95, maximum 80 tokens. Computer science, so this was the input context and instruction prompt. Computer science refers to science and computing methods, computers, hardware, software, applications. Also refer to research in many disciplines such as mathematics, computer science, computer engineering, science and computation, application of algorithms, programming, data analysis. Yeah, so sounds sensible. So we took pre-trained GPT-2 model and it was fine-tuned so that it understands what these prompts mean. It means given this kind of input, it needs to answer corresponding to these instructions. So after fine-tuning, we had some sensible outcomes from the model after fine-tuning. So this is it for the long hands-on tutorial on LLMs. From next time, we're going to switch back to the lecture series, and we're going to talk about various models like GANs, VAEs, diffusion models, and reinforcement learning, and it's going to get more theoretical. All right, that's it for today's lecture. Thanks.